Okay, the topic of this mini video lecture is transform boundaries, which is the last of the three types that we haven't discussed yet in class. So I'll lead into this with a bit of a clicker question. And you can see there at the top it says transform boundaries are commonly associated with oceanic ridges. So looking at this diagram, we've got red and yellow boundaries outlined. There are two different types. And so if you can pick out which one would be the divergent boundary and which one would be the transform boundary. So you can pause the video if you want to think about it. But if we actually look at this closely, we can see that sort of the uh, eastern side of the image, Africa here is moving right, South America and what's labeled as the South Atlantic Ocean here is moving left. And so the main divergence is occurring on either side of these yellow marks, which are going to be the divergent boundaries. And these are actually linked. The ridge isn't sort of a nicely smooth linear feature. It actually runs in this zigzag or stair-step pattern. And that's because as the divergence takes place on a spherical Earth, you create lots of these different fracture zones, and therefore the ridge sections get split and end up being connected by these horizontal fractures along which you have side-by-side motion. So these are transform boundaries associated with oceanic ridges. We can take a little bit closer look at a diagram here. So if we see A and B as the main plates diverging, here's our ridge section here and another ridge section here. It's not continuous. It's separated by a fracture zone along which there is side-to-side movement. And so if we label this, we can see we have a ridge, a transform boundary, and a ridge. So sort of a divergent boundary that is broken up in places by a transform boundary. We do have transform boundaries on a larger scale, other than just associated with oceanic ridges. One great example is the San Andreas Fault, shown in the image here in Southern California. And the San Andreas Fault is certainly poses significant geologic hazards in the sense that there's lots of earthquakes of all different sizes that are known to occur along the San Andreas Fault. However, it's a bit different than the Cascadia subduction zone to the north in the sense that the San Andreas Fault, it's only associated with side-by-side plate movement as the Pacific plate moves up here towards the northwest. And because of that, there's no magma being generated, so you don't have volcanoes along transform boundaries. Furthermore, the San Andreas Fault is on the continent, it's not in the ocean. So even if you have movement along this fault, you're not going to generate a tsunami in the same way that you might generate one along the subduction zone in the Pacific Northwest. So certainly a geologically active area, but the hazards are quite a bit different along the San Andreas Fault because it's a transform boundary as compared to the convergent boundary just north along the coast of British Columbia, Washington, and Oregon. One other thing to point out is the reason that you have different boundaries is because of what's known as a triple point. It's where three plates meet. And so this is a triple point right here that sort of separates the San Andreas Fault to the south from the Cascadia subduction zone to the north. And just a couple of pictures of the San Andreas Fault. So quite a significant feature. It looks like a scar running through the landscape. Again, no volcanic activity. You don't form huge mountain ranges, but you do have some local high topography, as you can see in the image, hills and different things like that. Another image. And so the last thing to talk about beyond transform boundaries is, now that we've covered all three types, is when you look at the map of tectonic plates, you can see according to the size of the white arrows that indicate different speeds of movement, there's actually quite a range of speeds at which the tectonic plates move. You can see there it says 1 to 15 centimeters per year, and so the question is, why do some plates move faster than others? If you want to pause the video and think about it, that's great. We're going to move on here and provide an explanation for this, which is the idea first of the concept of ridge push. And so the reason that some plates move is because at a divergent boundary, you have heat flow from the mantle. It generates a ridge because it's hot, the material is hot and therefore makes it buoyant. Because you have a ridge, you actually create a force in which the plate wants to move down and away from the ridge in response to sort of the gravitational tug of the material itself. This is a phenomenon known as ridge push. So if you have a divergent boundary along one side of a plate, it's going to be pushed by the ridge in that direction. At the same time, if you have an edge of a plate that is being pulled down a subduction zone, it's going to experience a force known as slab pull. It's because the crust is nice and heavy and dense down here. If it begins to subduct, it's going to tend to sort of pull the rest of the plate along with it. And so in this diagram here, we have ridge push pushing this plate to the left. Slab pull is also pulling this plate to the left, so chances are it's probably going to move pretty quickly in that direction. One thing to note that it's only the subducting plate that experiences the force of slab pull, as the overriding plate, since it's not actually going down in the subduction zone, doesn't experience this force. There's just a quick note there that says other forces such as convection in the mantle also play a role. This just refers to the fact that there may be varying degrees of heat flow at divergent boundaries and other places like that, which may affect the speed of plates as well. And so thinking about ridge push and slab pull, we can look at this map of tectonic plates and begin to look at the different plates and see if we can determine whether it's being moved as a consequence of ridge push, slab pull, or a combination of the two. And so we can start here in the African plate. And if we look all around the edges of the African plate, we can see that for the most part, as indicated by the white arrows and our general knowledge of plate tectonic boundaries, it's essentially surrounded by all divergent boundaries. What this means is that it's only going to experience ridge push. However, if we move over to the Australian Indian plate, for example, we can see there are divergent boundaries along its western and southern ends, but we also have a convergent boundary along its northern end, and because the island arc is up here on the Philippine plate, that tells me that the Australian Indian plate is the one being subducted or pulled down the subduction zone, so the Australian Indian plate is being moved by the processes of both ridge push and slab pull. And so you can go through this process with all the plates based on what's going on at their borders. You can see that we have some that are ridge push only and others that are ridge push and slab pull. So let's test this concept with the following question. If you'd like, you can pause the video and think about it. Otherwise, I'm going to continue along with the correct answer. So if we look at the South American plate, the correct answer here is ridge push. And the reason this is the correct answer is because we have the ridge, the Mid-Atlantic ridge on its eastern side, which is pushing the South American plate to the left. And if we go on the other boundaries of the South American plate along its west coast, it is indeed a convergent boundary with an associated subduction zone, but it's the Nazca plate that's subducting, whereas the South American plate is the overlying plate, and so then South American plate is not actually experiencing slab pull, so as a whole, it's only experiencing ridge push. We can do another clicker question about this, sort of thinking about in the grand scheme of things where different places are moving over time. So again, you can pause the video and think about this question. The correct answer here is New York and London. These two locations are splitting apart, moving further apart the divergent boundary in between them, versus Bombay and Sydney on the same plate. They're not going to be moving apart. Galapagos Island is moving closer to Rio de Janeiro because this is a convergent boundary here. And Tokyo and Hawaii are moving closer together as well. This is also a convergent boundary. Pacific plate is being pulled towards the northwest. Taking this a step further, we can think about, well, what oceans are growing or shrinking, which continents are most likely to collide next. You can kind of study this map, look at the different arrows. Well, is the Atlantic Ocean going to continue to expand, or is the Pacific Ocean going to expand, et cetera, et cetera? And this can lead into questions such as this one, which is what you think the distribution of continents will look like approximately 50 million years from now. Again, you can pause the video. But the correct answer here is A. So this is the only image which shows the North Atlantic Ocean sort of continuing to widen a little bit. We know this is a divergent boundary in the North Atlantic. And we actually see interesting here that Africa has collided with Europe, which we believe will take place as a result of its movement towards the northeast, even though we also do have a divergent boundary that may or may not continue to split Africa apart along this East African Rift Valley. D could potentially be correct a couple 100 million years in the future. Sort of is inevitable that we'll have another supercontinent at some point in the distant geologic future, but it's probably going to take quite a bit longer than 50 million years. Okay, that wraps up plate tectonics.